Hello, everyone. We are the research group of Associate Professor Junping Gen, Department of Electronics Engineering, Shanghai Jiao Tong University. My name is Kun Wang. Today, we will introduce a novel low-profile phased antenna with dual port and its application in 1D linear array to 2D scanning. All along, we want to solve two key problems. First, the radiation pattern of the antenna element is fixed, which operating mode is single, and the linear array are difficult to achieve wide-angle scanning. Second, based on the traditional principle of pattern multiplication, the 1D linear array can only scan in 1D space, which is difficult to achieve 2D scanning. Therefore, how to achieve the antenna element with continuous beam scanning characteristics and the array can scan in 2D space are important issues. To solve the above problems, we proposed a dual-port phased antenna based on SSPPS and two types of array. The radiation patch of the proposed phased antenna element, mainly composed of an N-shaped fishbone structure and a parasitic patch. The proposed phased antenna element has two feed points, and the phase difference between the two parts delta phi equals phi2 minus phi1. 7 shows the main beam of the radiation patterns of the proposed antenna element changed significantly with the phase difference between the two feed points. Figure 1 shows, based on the generalized principle of the pattern multiplication GPPM, the phase difference 2 can be applied to 1D linear array beam scanning. The main beam of the linear array not only along the theta direction, but also along the phi direction. That is to say, the 1D linear array can realize 2D scanning, and wide-angle beam scanning is realized in SOZ plane, YOZ plane, and SOY plane, respectively. Based on the GPPM and the phased antenna element, we construct two types of 1D linear arrays. These two 1D linear arrays can achieve wide-angle scanning along the theta direction and phi direction. Experiments show that the two proposed arrays have good radiation characteristics and wide-angle beam scanning performance in SOZ plane, YOZ plane, and SOY plane respectively. That's all. Thank you for watching. For more details, please click the DOI in the page.
What's hot in antennas and propagation? This video briefly introduces the article A Low-Cost Wideband Dual Circularly Polarized Aperiodic 2D Phased Array. The dual circularly polarized phased array is one of the effective methods to solve the multipath fading of the wireless channel. In addition, it achieves polarization multiplexing, to make more effective use of limited spectrum resources. Similar to traditional phased arrays, we anticipate that dual circularly polarized phased arrays will also have the great performances. To this problem, we will face the challenges of the contradiction between the bandwidth and isolation, narrow bandwidth of traditional patch, and the large element spacing causing grating lobes. In this paper, we introduce several key methods to realize a 2D dual circularly polarized, low-cost aperiodic array with bandwidth of 58% and plus or minus 45-degree scanning with low SLL. We design a new high-performance dual circularly polarized element using parasitic radiation, rotating feed, decoupling metal wall, composite feed network, and other techniques. The most notable features of this element are the realization of wide IBW and ARBW while maintaining high isolation, which has proven difficult in previous works. In addition, we propose an effective new optimization method for aperiodic array design, which saves more computing resources than the traditional genetic algorithm and able to solve various electromagnetic problems. Based on the proposed method, We use aperiodic methods to present low-cost thinking and solve the problem of grading lobes in the large spacing scanning process. The scanning performances of the prototype were verified by the measurement. It can achieve the characteristics of high gain and low side lobe. It eliminates grading lobes in traditional broadband large element spacing arrays and improves anti-interference performance. Its high gain and low loss characteristics contribute to energy savings and cost reduction. It has a wide range of applications and potential in many fields. In conclusion, first, a broadband high isolation dual circularly polarization element is proposed based on the method of designing broadband high isolation element and feeding circuit. Then, the broadband dual CP element is applied to the aperiodic array based on the proposed high efficiency aperiodic array design method. It can achieve the characteristics of high gain and low side lobe using the limited number of elements and TR modules. For further consideration, the element and the array can be further improved. The related paper has been published on IEEE Transactions on
We are glad to share you with our research, fully metallic millimeter wave lens array antenna for wide-angle beam scanning phased array. In this work, a lens array antenna based on 4 partial Maxwell fisheye (PMFE) lenses is proposed, which can obtain wide-angle beam scanning capability. The lens array is designed as a staggered up and down structure in the Y direction for the suitable element spacing, as we can see in Figure 2. Rectangular waveguides are placed along the QC focal line of the lens antenna as the feeder array. The working principle are as follows. The array pattern can be obtained by multiplying the array factor and the element factor of PMFE lens element. The beam steering of PMFE lens element can be realized by moving the waveguide feeder to the different position of the focal line. Besides, the array factors are determined by the phase difference of the adjacent element. If we adjust the suitable feeding position P and phase difference according to the scanning angle, the good beam scanning performance will be obtained. In addition, benefiting from the narrow beams and wide-angle beam scanning of PMFE lens element, the grading lobes can be suppressed, especially at large beam scanning angle. To miniaturize the lens element, the shaded parts of the full-size PMFE lens are cut and removed to reduce the lateral width of each lens. In addition, the full metallic PMFE lens is realized by the PPW loaded with the periodic metallic nail arrays on the top and bottom plates, whose height arrangement complies with the Green law of the MFE lens. A typical phase distributions are designed to mimic the corresponding phase shifting states. Each feeding network is composed of a microstrip 1:4 power divider as seen in Figure 1, to realize the phase difference between the lens elements. The prototype was fabricated by means of milling and assembled with screws. It can be seen that the reflection coefficients at the entire working band are all below -10 dB at different main beam directions. The simulated and measured results agree well. The same radiation performance may also be realized in the whole operating band. The BSR of H-plane from 0 degrees to 65.5 degrees and 3 dB BCR of ± 70.8 degrees is obtained with the SLLs below -8.0 dB. Meanwhile, good fan beam performance in the E-plane at 27, 28 and 29 GHz are obtained. At last, the measured and simulated gains are from 14.7 to 20.3 dBi and from 16.4 to 20.7 dBi, respectively. The aperture efficiency of the lens array antenna decreases from 75.9% to 21% due to the reduction of the equivalent aperture, especially at wide beam scanning angle. Thanks for watching.